So I'm really thrilled to be a part of this series, and a huge thanks to Jacob for the invitation. My talk today is based on recent work in which I build off of my PhD dissertation, where I analyze in great depth the black hole information loss paradox. And my goal is to apply that analysis with laser focus to evaluate whether there's potential for cross-fertilization with the measurement problem. And as my title indicates, I am skeptical that there is meaningful cross-fertilization because I'm going to argue that black hole information loss with Schrödinger's cat is not the measurement problem's problem. Okay, and so this work, like I said, is building off of what I had done under prior funding opportunities. So I just wanted to, have those acknowledgements. And the outline of my talk is going to look like this. I'm going to provide an overview of the historically conventional narrative of information loss. So this is how Hawking understood his derivation and basically launched the discourse. And then I'm going to ask the question whether, this concern over non-unitarity is really crying wolf. Could it actually be, an answer to another problem, namely, how should we interpret the foundations of quantum theory? Now, my answer to that, which I'm going to, give you the spoiler alert right now, is that no, non-unitarity is not the holy grail, because black holes are actually indifferent to the interpretation of quantum theory. And if we look more closely at Hawking's derivation, we realize that there are novel kinematic implications. So given that the problem doesn't have to do with modifying the equations of motion, it's really the kinematics that are going to come to the rescue. And I'm going to conclude with some takeaways about how we can understand the black hole information loss discourse in an interpretation neutral way. So I'm going to start by analyzing black hole information loss in terms of time irreversibility. I want to make sure that we're all on the same page. So here's a little bit of background of the formalism. And, if you're already comfortable, then, this is just going to be a review. There's something called operators that we use to figure out how quantum states are going to evolve. And there's a special class of them that are unitary, which have the special property of preserving purity and mixedness of states. So what does that mean? Well, pure quantum states are the most fine-grained description that we conceivably can have. And they encode probability distributions over measurement outcomes. So they possess maximum information about quantum systems. That includes information about superpositions of eigenvalues and the holistic correlations of entanglement. They're also represented as vectors in a multidimensional Hilbert space or as complex wave functions. On the other hand, mixed states are often thought of as incomplete or coarse-grained quantum states because they encode probability distributions over pure states and they possess incomplete information about quantum systems. So they're used to describe entangled subsystems, for example, but they don't retain memory of the holistic correlations. And they're also used to describe statistical ensembles, which are very useful when thought of as macro states. So this is just a little bit of background, but the main takeaway is that unitary operators take pure states to pure states. They also take mixed states to mixed states, but we're going to have something unprecedented happen in Hawking's derivation of black hole evaporation. Oh, and in contrast to pure states, they're represented as density matrices or as multidimensional Hilbert spaces in and of themselves. So with that, you know, technical machinery under our grasp, I'm going to talk to you a little bit about quantum field theory on curved space-time, although in very intuitive, heuristic terms, so that we can figure out what's going on with black holes. So the framework of Hawking's derivation, which is what he described in his 1975 and 1976 papers, is that he took a classical geometry of a vacuum black hole solution, such as the Schwarzschild metric, and then he imposed quantum matter fields satisfying vacuum conditions on that background space-time. So of course, right, they need to match, where we're assuming for the time being that whatever matter that formed the black hole has already, become part of the metric, and we are neglecting the initial collapse and formation process. This may sound like a very boring universe, given the number of times I've used the word vacuum in there, but it's actually quite interesting. Because what he showed is that if you decompose the solution into field modes that come in positive and negative frequencies, you can form a picture of entangled virtual particles that cancel each other out. And when you have an event horizon and a singularity, some pretty novel things happen. So here's a schematic that I think is, very pedagogical. Although the picture of particle fluctuations isn't necessary to the story, I think it does capture the core of what's relevant. So we can think of the production of Hawking radiation as coming about through these Hawking pairs. We have positive energy partners, which are depicted in blue, and negative energy partners that are depicted in green. So these are entangled pairs, but when you have an event horizon that potentially separates these pairs, what happens is that some of them get trapped inside the black hole. And if those are the negative energy partners, that corresponds to a reduction in the black hole's mass. And what you have left at future infinity are solely the positive energy quanta. So that's what we think of as Hawking radiation. And, thus far, because we're on a semi-classical space-time, the space-time itself is classical, and it's just the matter fields that are quantum, we still have a singularity, and as we would expect, world lines end at the singularity in finite time. So as I just described, the separation of Hawking pairs by the event horizon results in global energy flux. Although Hawking didn't directly calculate this, he inferred it as the most reasonable conclusion if we were to stipulate energy conservation. Although subsequently, there have been more detailed derivations in that vein. And what's unique about the energy spectrum, or the state of late-time Hawking radiation, is that it's thermal. And thermal states are represented by density matrices because they're mixed. So therefore, we have a non-unitary process. Pre-evaporation states are pure. They include the black hole interior in the description, and they also encode complete information about the entanglement structure of Hawking pairs. But as I just mentioned, post-evaporation states are mixed. And that's because, as you would probably expect, when something evaporates, right, the system that started out has been converted into radiation. And if we think something similar is going on here, the final states don't include the black hole in the description anymore. And it actually now encodes incomplete information about the vestigial radiation that's comprised solely of positive energy quanta. So I'm not going to go into too much detail about why, we think that the states are mixed, beyond the fact that the radiation looks exactly thermal. But if I have time, I'm going to delve a little bit more into this question about what it means that information is complete with respect to entanglement. But for most of my argument, we don't have to worry about that too much. So one thing to note, though, is that the memory of non-local correlations between the positive and negative energy partners seems to have been erased at this point. Now, what's the mainstream narrative? Why have so many people, become extremely uncomfortable by this type of evolution? Well, one, it seems that we get the same final mixed state for any perturbation of the initial pure state. And that follows from the fact that the radiation has a thermal spectrum. We can explain this because not all of the information about the internal configuration of the black hole is making it out to future infinity. And that should be perfectly explainable because there's an event horizon. General relativity tells us that the event horizon is a causal boundary. Nothing that travels at or slower than the speed of light can escape. And we can also explain the thermality of Hawking radiation because it obeys the no-hair theorem. So the most information it can contain are three parameters: the mass, electric charge, and angular momentum of the black hole. So, maybe it's not the no-hair theorem, it's the three-hair theorem. But the point is that classically, black holes are basically bald. And as long as causality is respected, the radiation is not going to tell you anything about what went inside. So information is lost about whatever was trapped in the black hole, especially after it disappears. So what we have going on is a form of indeterminism or time irreversibility, and global non-unitarity signals information loss because of these attributes. And I'm going to go into a little more, I guess, of a justification as to how these concepts are related. So although, with due skepticism, that's the word I'm looking for, philosophers have pushed back against the appropriation of the word information to characterize what's going on. I think there is, a relevant usage for it. I'm not going to give you the best usage for the, phrase information loss or information conservation. But there is a pretty intuitive sense in which state specification involves a certain amount of information. And what deterministic laws do, such as unitary evolution, is they give you one-to-one maps that tell you how one state uniquely evolves into another state. So information is conserved in state specification because of perfect recoverability, where if I want to go from point A to point B, I can also go from point B to point A, and my map is going to tell me how that works. However, when you lose perfect recoverability, you now have indeterministic evolution. And this takes the form of one-to-many maps in which point A can take me to point B or point C. And it can also take the form of many-to-one maps where I can get to point B either by starting at point C or by point A. And therefore, information is not conserved because depending on what side of the map we start on, we may not necessarily recover the states on the other side of the map. So this is, the somewhat loose connection between information conservation or loss and deterministic and indeterministic laws. So why is this important? Well, there's a version of the black hole information loss paradox that is worried about this connection. And, according to my work, I'm going to call this the unsophisticated version. So we have two horns of a dilemma. The first is that quantum systems supposedly evolve unitarily. And then there's an auxiliary premise that is very relevant to this first horn of the dilemma, where only unitary evolution conserves information, because it's unitary evolution that involves deterministic one-to-one maps. The second horn of the dilemma, which is the third premise of the paradox, is that quantum matter fields on black hole spacetimes evolve non-unitarily. So obviously there's a contradiction between premise 1 and premise 3, which is why there are two horns of a dilemma. And the way to get out of the paradox is to either give up on the first premise, we accept non-unitary evolution, and as a corollary, we would also have to accept that information is lost, because that's what premise 2 tells us. On the other hand, we can decide to get rid of the third premise and insist that somehow we have to accommodate black hole evaporation within a unitary framework. So that begs the question, how do we choose which premise to keep and which premise to give up? And, of course, the title of my talk is based on exploring what happens if we give up on unitarity as a premise. So the reason we might think that we should give up on the first premise is because, as articulated, the paradox does not come off as interpretation neutral. And the reality of the discourse has been that supposed solutions have emphasized the implausibility of non-unitary evolution. The reasons they give are that we're bound to a semi-classical framework within Hopkins' calculation, but that's not going to be a final theory. We think that quantum gravity is going to come in, and it's going to give a complete story about what happens in Planckian regimes of very short distances and very high energies. And this is crucial to the account of black hole evaporation, because we want to know what happens in the large curvature region near the singularity. We want to know what happens during late stages of evaporation, whether Hawking was right or not, when the black hole becomes extremely small and the temperature of Hawking radiation involves tremendously high energies. And then depending on other commitments that you have, you might even think that quantum gravity bears on the horizon structure. Perhaps the no-hair theorem is just an approximation, and there are in fact a lot more degrees of freedom to be had. So, Crowther has analyzed the role of guiding principles in the development and provisional acceptance of quantum gravity, and it's clear that unitarity is serving as a guiding principle. So picking premise 1 in favor of premise 3 is really a stance on how quantum gravity should emerge, and how black hole evaporation should look like within a theory of quantum gravity. Yet there are some people, and I am responding heavily to Ocon and Sudarsky, that are dissatisfied with this trend in the discourse, because they argue that information loss presupposes a particular interpretation of quantum theory, namely many worlds or Everett. And they also are quite skeptical that this is the best interpretation of quantum theory that we have so far. I mean, they go so far as to say that it's the most contentious interpretation, which I think is a little optimistic. I'm not sure how Bohmian mechanics is doing these days, but whatever the relative weights are of the interpretation, right, it seems pretty fishy that we need to be relying on an interpretation at all to make sense of the black hole information loss paradox. And the question is, why is many worlds or Everett driving the discourse? So they're going to push back, and they're going to remind us of the measurement problem. And as adapted from Maudlin, the measurement problem can very cleanly be formulated as the horns of a trilemma. So the first premise is that quantum systems evolve unitarily. If you notice, this is exactly the same premise that we had in the unsophisticated black hole information loss paradox. The second premise is that quantum states are descriptively complete. And the third premise is that measurement outcomes are determinate. So I'm sure as many of you are familiar, we arrive at different interpretations of quantum theory depending on which of these premises we reject. We can reject the first one, and in doing so, we basically establish that we need some sort of non-unitary mechanism to deliver 2 and 3, or we can deny the second premise, and that's basically inviting hidden variables because we need to add something to the unitary evolution. And then finally, we can deny the third premise, and this is how we end up with many worlds because, right, what we thought were determinate outcomes are really branch specific. And this can be depicted with Schrödinger's cat. So dynamical collapse involves definite measurement outcomes because of some dynamical process, such as an interaction. Then we have hidden variables, where Schrödinger's cat was in this picture alive the whole time. We just didn't have the resources to find that out. And then finally, we have many worlds where the state of Schrödinger's cat depends on what branch of the superposition we're living on. And so here's the observation that Ocon and Sudarsky make. If unitarity is universally broken and information is generically lost, then the fact that black holes lose information stops being that surprising and problematic. So what they've noticed is that if we commit to one of the interpretations of the measurement problem, namely, if we deny the first premise and we accept a dynamical collapse model in which the laws of quantum theory are complete and measurement outcomes are determinate, or better put, quantum states are descriptively complete, then we realize we are simultaneously rejecting the first premise of the unsophisticated black hole information loss paradox. And this is exciting because we now have justification for keeping premise 3, where black hole evaporation is non-unitary, and we're getting a 2-for-1 deal. We're solving 2 paradoxes for the price of 1. So they surmise that, because we can solve 2 problems in one fell swoop, then it makes sense to conceive of unitarity as the weak link, and that's what motivates us to give it up. So they have an argument that runs something like this. Quantum systems evolve non-unitarily if we accept dynamical collapse as the most promising interpretation of quantum theory. And black holes are quantum systems as well. We don't have to take this too literally. We can even modify this or qualify this with the statement that quantum matter fields are, confined in black holes, and therefore we can treat the entire system, as if it were quantum. That's not going to make or break what they want to do. But the conclusion is that black holes must evolve non-unitarily as well, because this appears to be a particular instance of a universal phenomenon. And now there's no mystery as to why there's information loss, because we already realized that non-unitarity loses information with the one-to-many or the many-to-one maps. So let me, motivate that a little further with what's going on when we try to integrate dynamical collapse with black hole evaporation. Penrose had a pretty intriguing idea where he wanted to, see if he could come up with a propensity for collapse that wasn't just purely random. So to give you a definition, in case you're not quite clear what it means for non-unitarity to be linked to collapse. It involves an abrupt physical process of probabilistically transitioning from a superposition of measurement outcomes to a determinate one. This is, a dirty definition that I think does very well for what we're going to analyze next. But the key words here are abrupt and probabilistically. So that's how you know that this can't be deterministic and that this is not going to involve one-to-one maps. Now, his proposal is to link dynamical collapse with space-time structure. And he proposes a trigger in the form of the magnitude of space-time curvature. So basically, the larger the curvature, the idea is that the more likely it is for the quantum system to collapse into, one of the measurement outcomes that it may have been in a superposition of prior to that point. And the explanation for black hole information loss is that these are very large curvature regions, especially as you approach the singularity, and therefore the frequency of collapse events is going to increase. Now, I hope you're confused at this point, because this story is very different from the one I told about Hawking pairs getting separated by the event horizon, where some of them escape and some of them are annihilated by the singularity. And I hope you share my sentiment of, whoa, hold your horses. There were never any collapse events in Hawking's derivation to begin with. So a fallacy has been committed in the argument that dynamical collapse explains non-unitary black hole evaporation. And the fallacy is that of uniqueness. The argument that quantum systems evolving unitarily explains black holes evolving non-unitarily only goes through if non-unitary evolution is a unique process. But a closer look at black hole evaporation reveals that it's not a unique process. And the reasons for non-unitarity in the two cases are actually orthogonal to one another. I'm going to argue that what's happening in the black hole case has to do with kinematics, and what's happening in the dynamical collapse case, as its name suggests, has to do with the equations of motion. So this is why my answer is no to the question of whether non-unitarity can be the holy grail. And I'm going to just go through, and flesh out where the reasoning went wrong to motivate that black holes are actually indifferent to the measurement problem. So you might have thought that, right, you could get away with this sort of cross-fertilization between the two paradoxes because both types of evolution involve many-to-one maps. Black hole evaporation involves many-to-one maps since different internal configurations of the black hole lead to the same thermal radiation state. And as a result, information is lost about prior states and their built-in probability distributions. Now, it's also true that dynamical collapse involves many-to-one maps, and this is because of chanciness. So different superpositions can transition to the same measurement outcome. If you have different pure states with different amplitudes, but overlapping measurement outcomes, right, you get exactly this many-to-one map. There are, however, important differences between the two cases. And I'm going to be charitable and surmise that, Penrose, Ocon, and Sudarsky are aware of these differences and they seek to exploit them. So a huge difference is that dynamical collapse involves not just many-to-one maps, but one-to-many maps as well. And again, the reason is chanciness. And that's because the same superposition can transition to different measurement outcomes. Which is, very simple when we think of Schrödinger's cat. Is it dead or alive? Well, if we are going to say that it acquires a definite state upon some sort of dynamical transition, then it can be either dead or alive. And, what actually obtains is going to be probabilistic. So this means that black hole evaporation, unlike dynamical collapse, is time asymmetric because the past is washed away. So it seems like there's an arrow of time. I'm not going to get into a discussion about the arrow of time, but some people did think this was an exciting development for that debate, precisely because, right, we can't recover what the original black hole was like just by time reversing the state of radiation. This is in contrast to dynamical collapse, which on one conception is time symmetric, not time reversal invariant, because the past and future are both washed away. So the many-to-one and one-to-many maps make it the case that you really lose information in both temporal directions. And prima facie, this seems to make the problem worse. But Penrose, Ocon, and Sudarsky want to convince us that it actually makes the situation better, and they have an account of effective information conservation. Although the reasoning is specious, what they want to do is say that adding dynamical collapse to black hole evaporation removes the time asymmetry and can restore information for all intents and purposes. So, as I discussed before, information is strictly lost towards the past and the future in the short term because we have non-unitarity in both directions. But it can be approximately recovered in the long term because of the net compensation of many-to-one maps by one-to-many maps. What does that mean? So if you look at the evolution, in a system that involves dynamical collapse over a long enough period of time, you're going to notice that it looks like there's a time average constancy of input and output states. You have one-to-many maps, which we saw before, and then you also have many-to-one maps. So over a sufficiently long period of time, you can approximate the combination of these maps as symmetric many-to-many maps. And here it seems like, given the states on one side, we can retrieve all the states on the other side. So I like to think of this as a smeared out determinism for all intents and purposes. And for those of you that are well versed in statistical mechanics and phase space, the argument is that the indeterministic one-to-many map basically increases phase space volume. And then conversely, the indeterministic many-to-one map decreases phase space volume. So over long enough time periods, you basically have an average constancy of phase space volume, and that's what they're using to motivate information conservation, at least effectively. So what we want to do is figure out whether this kind of situation actually holds for black holes. And the fact is it doesn't, because they're forgetting about the novel kinematic implications of black hole evaporation. So I'm going to summarize intuitively why it doesn't work, and then I'm going to briefly explain the Penrose diagram. The simple fact is that the black hole interior disappears, and therefore, so does its states. The reason the black hole interior disappears, other than what's considered a normal evaporation outcome, is the global space-time structure, especially the role of the singularity. So there's a relation between infalling systems being trapped and destroyed behind the horizon and the fact that we lose states post-evaporation. So the singularity's annihilating effects and the final evaporation event take place in finite time. In this diagram, I apologize if you've never seen a Penrose diagram before, but very quickly, What it's trying to show is light cone structure of an evaporation spacetime. The diagonal dashed line is the black hole event horizon. Everything behind that is the black hole interior. The jagged line is the singularity, and E is the final evaporation event. So what we want to do is we want to compare pre-evaporation states. That's given by sigma 1 and sigma 2. And on these states, I've depicted the positive and negative energy particles. And then the post-evaporation states are depicted as sigma 3 and sigma 4. And just very crudely, you can see that the late time states, right, seem to have lost elements of the ontology. They're only left with the red dots. These are the positive energy partners. And, it's just a matter of logic that there's no way you can get these symmetric many-to-many maps when the post-evaporation states have fewer degrees of freedom. So that's the gist of the kinematic novelties of black hole evaporation. And I'd be happy to discuss this further during the Q&A if I'm going a little too quickly right now. But this is the idea. You have a pretty unique, pretty unprecedented global space-time structure, and that's basically causing your state space to be unstable over time. Therefore, symmetric many-to-many maps are off the table because we're actually reducing the dimensionality of your state space from pre to post evaporation, where we start out with, rather than kind of the simplistic maps I had depicted earlier, right? You have a globe, and the states in the globe, take up three-dimensional volume. So that's your state space in the beginning, but the map takes you to a lower dimensional sort of a lower dimensional manifold. It's as if we've squashed the globe into a two-dimensional map. And of course, there's no way you can even effectively conserve information because you've lost an entire axis along which you were encoding information about states. So non-unitarity in the black hole evaporation case arises due to modal instability. You're losing possibilities, and the point of time irreversibility is that they can't be recovered once the black hole is gone. So this is a consequence of global topological structure. Therefore, non-unitarity in black hole evaporation has nothing to do with modifying the equations of motion, which is what solving the measurement problem calls for. And no interpretation of our beloved feline mitigates eliminating elements of the ontology. So, if you're inclined to metaphysically interpret black hole evaporation, this is actually a really interesting opportunity given the instability of the elements of the ontology. And the lesson to be learned is that if Schrödinger's cat falls down a black hole, information is lost because it's erased from existence, essentially. It doesn't matter if it's in a superposition. It doesn't matter if it collapses into a state of being dead or alive. And it doesn't matter if it was always in such a state because, hidden variables, right, ensure that that's what it was from the beginning. What's happening in black hole evaporation has to do with global kinematic constraints. And this is why I think that Leonard Susskind, one of the foremost champions of resolving the unsophisticated black hole information loss paradox, at least in the way he talked, is that all hell would break loose in all of physics, not just black hole physics, once the door to information loss was opened. And as you can see, right, this is a much, much stronger sentiment than if we thought the unitarity of black hole evaporation was, of the same flavor as dynamical collapse, because of course, we're used to that every day in the laboratory whenever we make measurements. Now that I've laid out the problem, What is the solution? Well, a kinematic problem demands a kinematic solution, and that would be to conserve total degrees of freedom. So one option is if you start out with a globe, then you better end up with a globe post-evaporation. Alternatively, if we saw that we ended up with a projection of a map, and I don't mean projection here in the quantum sense, I just mean it's lower dimensional, then maybe we overestimated how many degrees of freedom we started out with. And in fact, we need to come up with a story about how there are fewer degrees of freedom than what were initially apparent in Hawking's calculation. So the way you do that is you have to modify the diagram that he proposed, and that's most likely going to come from high energy quantum gravity corrections. In order to pursue the first strategy, where you go from a globe to a globe, you would need to make sure that the black hole sticks around in some way, shape, or form so that it doesn't truly disappear at the end of evaporation. You need an additional byproduct. You can pursue singularity resolution, and that's going to give you some sort of remnant. You might pair that with halting the evaporation of the black hole when it reaches Planck scales. So that's going to give you the top scenario. However, if you're more persuaded by the bottom scenario, you're going to need to figure out a way to get whatever was trapped inside the black hole out into the radiation. And so you're going to be more focused on, giving a deeper story about the black hole event horizon that's going to be hairy and is going to show that the no-hair theorem was merely an approximation. So again, I'm going kind of very quickly, but this is just, the sketch of the strategies available to you to resolve non-unitary black hole evaporation in a way that is true to its novel kinematic implications. And as you see, these strategies are independent of what stance you can take on the measurement problem. So, right, the solution that I'm proposing here is agnostic about the dynamics. In both scenarios, globe to globe or map to map, like two-dimensional map to two-dimensional map as just a shortcut for visualizing it, you can have deterministic unitary one-to-one maps that take you from A to B and back from B to A. But it's also compatible with exactly what Penrose, Ocon, and Sudarsky want, which is a symmetric many-to-many map. And so I claim that, we can incorporate their suggestions, we can be inclusive in an interpretation neutral way if we reconceptualize information conservation as conserving degrees of freedom, because that's going to be independent of the dynamics. And both strict conservation and effective conservation are equally valid ways of solving the paradox. And I didn't give you a way to make it a little more sophisticated than the original version, but this shows you why it was a red herring to just decry, non-unitarity full stop. Right? We needed a little more nuance, and then we see that unitarity is not the only answer when we go about resolving it. So let me just quickly check how I'm doing on time. I think, if anyone is interested in a more robust formulation of the black hole information loss paradox, maybe we can do that in Q&A. But I'm going to, just wrap up and then, introduce a totally new kind of argument and see how you respond to that. So my main conclusion is that interpretation neutrality is in fact possible with the black hole information loss discourse, and it should be the default. Because as I have reiterated many times now, black hole information loss is a kinematic problem demanding a kinematic solution, and pursuit-worthy proposals address the more robust version of the paradox that I call phantom entanglement by stabilizing the overarching state space. And I'd be very happy to discuss phantom entanglement further if anyone is interested in what that looks like and how that relates to a kinematic problem demanding a kinematic solution. What's really strong about this way of characterizing black hole evaporation is that we can decouple the non-unitarity that obtains from the measurement problem, because the measurement problem bears directly on dynamics. It's about ensuring determinate measurement outcomes, and that's going to involve some sort of transition that departs from the Schrödinger equation. So unitary and non-unitary equations of motion are both compatible with information conservation. And here, to me, it's equally good to have strict information conservation or effective information conservation, which is why I'm going to leave you with the final thought that if you were, dissatisfied with the hegemony of, the many worlds interpretation or Everettian ways of understanding black hole information loss, right? The correct response to the observed hegemony is to challenge it, and it's not to replace it's not to replace many worlds with another interpretation like that of dynamical collapse that just takes its place in the hegemonic sort of treatment of the physics. So, I hope that I have, at least through all of the technical complexities, showed you through my various pictures how we can all care about black hole information loss, no matter what you think Schrödinger's cat is doing as it's falling down the black hole or hovering outside the space-time, observing and collecting Hawking radiation. And the black hole discourse, of course, shouldn't prematurely adjudicate on the measurement problem, right? We want the reverse to be true. We want to have good grounds for privileging certain interpretations over others and then integrating that into solutions to the black hole information loss paradox. So thank you very much for your attention, and I'm looking forward to your questions.
All right, so we're about to begin the discussion Q&A. If people would like to raise their hands using the participants tool, the participants window, please go ahead and do so. I thought maybe I saw a hand just before the break. Okay, we have a hand from a couple people. So Wayne had raised his hand just before the break. So Wayne, I'll let you go first, and then I have Lev next. Wayne, please go ahead.
Okay. Yes, well, thank you, Saakshi. This was very clear, and I think your conclusion is absolutely right. The black hole information paradox is not the measurement problem's problem. I'm not, okay, this isn't my expertise. I just want to know, you probably know that a couple of years ago, Tim Maudlin put a paper on the archive saying there's no there's really no paradox. And what Tim was focusing on is the, oh good, you've got the slide up, quantum systems evolve unitarily, and that's short form for between Cauchy surfaces, right? If I evolve a system from something, from a Cauchy surface to something that's not a Cauchy surface, that's essentially, tracing out degrees of freedom, and I don't expect it to. So, what Tim was emphasizing is very often people compare, like in this diagram you have here, evolution from a Cauchy surface to something after the evaporation that isn't. So, so what? And other people have said that no, that's true, but there's still a paradox there. And nonetheless, so I guess wondering what your take on all that is.
So that actually fits perfectly with how I think a true paradox does emerge if you ask the question, why is late time Hawking radiation mixed, and what is the interpretation of that? So while it's certainly true that you have Cauchy to non-globally hyperbolic sort of effects that are directly tied into the non-unitarity of black hole evaporation, entanglement plays a crucial story because, okay, I think I'm getting ahead of myself. Entanglement is a crucial part of the story because, in classical general relativity, non-global hyperbolicity would not necessarily be seen as contradictory or involving a paradox. I mean, you might have different presuppositions as to whether that's physically reasonable, but it's really, the quantum matter fields that change the game and raise the stakes. And the idea is that on the Cauchy surfaces, right, we can define quantum states that encode the entanglement structure between the positive and negative energy members of Hawking pairs. But once the black hole evaporates and we're left with the partial Cauchy surfaces, sigma 3 and sigma 4, it seems like late time Hawking radiation is in a mixed state because it's still somehow remembering that it was entangled with another system, but because of global non-hyperbolicity, that's you can no longer define quantum states that include that system. And I think Tim, even though he didn't acknowledge it, he was responding to that question, right? Hawking radiation is mixed. It seems like it's mixed because it's remembering itself as an entangled subsystem. What system is it entangled with? And he wants to give a story saying that no, you can actually find a way to foliate the space-time such that you have global hyperbolicity after all. I'm not going to comment on whether that's a plausible strategy because there's vehement disagreement on that, but it really comes down to, what are you going to do to deal with that stray entanglement at the end? Are you going to say that there's an additional byproduct of evaporation, a remnant, if you will, that purifies the mixed state at the end? And that's one way of restoring the Cauchy surfaces. You're basically finding a way to complete sigma 3 and sigma 4 with the black hole interior. So you can imagine extending the black hole into a baby universe through singularity resolution. The other thing you can do, which is consonant with the second strategy over here, is say, well, we just overestimated how many degrees of freedom there were to begin with, which means what we were calling Cauchy surfaces, sigma 1 and sigma 2, have a redundancy in them. It's really sigma 3 and sigma 4 that should be treated as Cauchy surfaces, and sigma 1 and sigma 2 are basically giving you too much information, right? Not all of the degrees of freedom on sigma 1 and sigma 2 are independent, and this gives rise to the alternative of getting information out of the black hole, and that's associated not with remnants but with holography. So this is, I think, a really interesting connection between kinematics, information, and black hole thermodynamics and statistical mechanics, because depending on which strategy you choose, you're saying something about how big a black hole can really be, and that's tied to interpretations of Bekenstein-Hawking entropy. So that's like a really quick rundown of how I think, right, these other issues tie into your question. And if you'll permit me, I'm just gonna kind of give it to you as is. I think the contradiction that really is to be had is the fact that Hawking radiation seems like it's a global system because it's all that's left, but it's also an entangled subsystem. And, in that sense, it's as if it were entangled with a phantom. So the way you get around that is you either, commit to it as an entangled subsystem, and then you have to basically say you start from a globe, you end with the globe, and that's compatible with baby universes, Maudlin's proposal, which is a form of baby universe, stable remnants, decaying remnants, and the works. Or you say that Hawking radiation is a global system. The mixed state at the end is really just a way of coarse graining, but it's not actually due to entanglement. And then this leads to proposals such as stretched horizons, firewalls, wormholes, and things of that nature.
Thanks. A lot to think about there.
Yeah.
Thanks, Wayne. Actually, I have a small follow-up to that question. So there's a really lovely review paper, review and more than review, a research paper, right, by David Wallace, that he wrote after Tim Maudlin's paper, questioning, the basis for calling it a paradox. And I highly recommend it. It's got a lot of really interesting information. Saakshi, I'm sure you've seen this as well. And the argument that David Wallace gives and that other people, I think, have given in response to Tim Maudlin's argument is to acknowledge that, yes, Tim Maudlin basically does have it right in the sense that there is a good argument that evolution between non-Cauchy hypersurfaces doesn't have to be unitary, but that the black hole information paradox has other parts to it that you can't explain away that easily. And one of them is the page curve. So if you draw a plot of the entanglement entropy that you expect, say, an ordinary non-black hole evaporating object to have. So suppose you've got like a lump of very hot coal and it's burning, and as it's burning, quanta are escaping. And you calculate basically the entanglement entropy of the escaping radiation. And what you find is that you get more and more entanglement entropy up until about halfway through the evaporation process. And then it turns over and begins to go down again because eventually there's nothing left for the evaporating radiation to be entangled with. The expectation is that a black hole evaporating according to the rules of quantum mechanics should show that sort of behavior at least well before you get to the evaporation point when you could be asking whether there's a problem with Cauchy hypersurfaces. So one would expect that while the black hole is still substantially there, that there's this moment called the page time when the curve, the page curve, the plot, the hypothetical plot of the entanglement entropy just begins to turn over. And that turnover point is supposed to be roughly halfway through the evaporation process. That's well before the black hole is fully evaporated. Presumably, we're still evolving between Cauchy hypersurfaces, and yet Hawking's naive calculation doesn't show the turnover. You get what looks like continued entropy growth indefinitely. And so part of the black hole information problem, part of resolving it, is hopefully accounting for the page curve, which again shows a deviation from Hawking's calculation well before the black hole is fully evaporated. And some of the exciting work coming out now from some of the groups working on trying to understand black hole evaporation through holography, and now there's some really interesting work that's been going on with 1+1 dimensional spacetimes, and working with Euclidean wormholes. There's all this sort of exciting stuff coming out. Part of the goal is is to replicate the page curve, find a first principles argument for why you get the correct turnover at that page time in the entanglement entropy. So this gives a somewhat more robust response to Malden that sort of accepts that he was sort of partially right, but also I think complicates the argument that he was making. And again, I highly recommend David Wallace's article on this. I don't know if I can locate the reference to it, but bears some thought on this discussion.
If I can just corroborate, Jacob, what you were saying, and I've pulled up the very curves you were talking about, right? We see that the entropy of the black hole is going down as it's evaporating because it's getting smaller and smaller, but as more Hawking pairs are produced, we see that the entropy of the radiation is increasing, and that seems to coincide with the entanglement entropy between the black hole and the radiation. And after this page time where it seems like, the black hole is as small as it can be to support the entanglement with the radiation, we get this inexplicable unbounded growth. And this is related to what I was talking about with the instability of degrees of freedom. Hawking radiation is sort of behaving.
Saakshi, sorry to interrupt, but are you doing this on a slide? There's a comment. It looks like we're not seeing the slide you're on, or are you just...
okay. Yeah, sorry. Maybe I need to. Sorry about that.
It looked like you were tracing the curve with your mouse pointer, but I don't think.
There we go.
That's it. Perfect.
I just had to switch the presentation. So this is the curve that Jacob was talking about that illustrates what I'm calling phantom entanglement, where the entropy of the black hole is going down, the entropy of the radiation is going up. This intersection at the page time suggests that that's the maximum point, that's the smallest the black hole can get to fully support the entanglement with the radiation. But for some reason the entanglement continues to grow even as the black hole gets smaller. And I think this is related to what I was trying to highlight with the instability of degrees of freedom, where the radiation is what's left, but it's acting in a way as if the black hole is still around, even though we're losing black hole degrees of freedom. That's where the instability is coming from. And, in order to satisfactorily address this problem, it maps onto the two strategies that I proffered, right? Either you say there is not truly a gap in degrees of freedom. And how do you do that? You say, well, there are more degrees of freedom of the black hole than what's being shown by this curve. That's the globe to globe strategy, the remnant baby universe type proposal. You have to allow for the interior to be kind of as big as you need it to be to purify the radiation. And in fact, that is, I think, what Penrose would have been happiest with, right? When he talks about information being lost in black holes because you have this increase of collapse events as you get closer and closer to these high curvature regions, right? He's imagining that the black hole itself can store an unbounded amount of information. And that's what Ocon and Sudarsky are building off of. So implicitly, right, they are assuming the globe to globe map and then integrating collapse within that story. Alternatively, which is what David Wallace is concerned about, if you say no, black hole entropy is bounded, in fact, by its thermodynamic entropy, which is what's being shown here, then this purple curve, which is the entanglement, it has to turn around, and it's going to turn around after the page time. And what we're seeing of the mixed radiation state is just its coarse-grained thermodynamic entropy. So, that's how I think the story that I've given, although I put less, emphasis on this aspect, fits exactly with what Jacob, brought our attention to.
Great, thanks. Totally agreed. And I put a link to the paper again in the chat for those who'd like to see it. All right, so the next hand is Lev. Lev, please go ahead.
Thank you for the talk. And if people know me, I like disagreement. So I thank you because I disagree.
Okay.
I have a kind of a sketch. I never really looked very careful on the problem, but my sketch of the solution of this information loss paradox is really measurement problem. And so your thesis is opposite, so disagreement. And this is, for me, it's interesting. First, I'm not sure I fully understood why you don't like the connection. If there is a collapse, clearly there is a loss of information. And if there is a loss of information, so there is no paradox because information should not be conserved. In your talk, you said that there is some difference between collapse. The mechanism is different, okay, but the fact that we should keep the information then disappears in both cases. But of course, I'm not in this. I don't believe in any loss of information. I don't believe unitary is a whole grain. So unitary cannot be broken from my point of view. And I believe that if you keep unitarity, then you kind of understand what's going on in this unitarity puzzle, because Hawking is not careful. The evaporation process is a quantum process. So we don't know, it's happened in different times. And usually when people make this calculation of information, they consider one word before and one word later. But what's happening is there is one word before and there are many words later. All of them have thermal information, but this thermal information have different size. One evaporated now and one evaporated later. And so we have a lot of place of relative phase between these different branches, different times of evaporation, to keep the initial information. So there is no kind of robust paradox, and this is solved by many words. So usually the many words make allows the paradox. I think this allows the solution of the paradox.
Okay, well, thank you so much for making me work for it. I completely agree with you that information conservation in the many worlds certainly can't be confined, right, to a world line across branches. Information is conserved in the wave function at large, and in any given branch, right, you would not expect unitary black hole evaporation at all. And this is a point that was made by Sean Carroll, who I think is in the audience, along with some collaborators. So, that point is completely well taken. But what I do want to distinguish is, the desire, which I think is fallacious, to say that, black hole information loss is solved by solving the measurement problem. So yes, you may have this a priori stance where information loss is not a problem for you because it certainly is the case that collapse theories, right, are incompatible with one-to-one maps that perfectly preserve state specification, where you have perfect retrievability from the initial to the final and the final to the initial. But what you can't do is say that your collapse theory is going to explain why black hole evaporation is non-unitary in Hawking's original calculation. Now, what you're more than welcome to do, because you said that ultimately you think unitarity can't be broken, is you can tell me why Hawking was wrong, and it seems like that's what you have in mind, where something about his calculation needs to be modified so that global evolution is unitary, and then information loss, right, is not because of this strange changing of Hilbert spaces where right? Your initial Hilbert space was much larger than your final one. It has more to do with the measurement problem and the fact that on any given branch, it looks like there was collapse of the wave function. So please tell me if I'm sort of, understanding how you're envisioning the role of information loss here.
Essentially, now we are very close to agreement. So I think it's, yes. So I agree that there is a different type of, I agree. First, it's very difficult for me to talk about collapse because it's unthinkable. But I agree that collapse doesn't resolve Hawking paradox. This is true. But since I don't believe that there is a solution of measurement problem is collapse, solution is many words. Many words for me does resolve it. And the statement, this statement I made many times and I talked to Don Page. He said that maybe it works. I don't know. But again, I never worked carefully on this. So if I worked on this before and make it kind of robust, it will be interesting if he will make a comment.
All right, thanks, Lev. I don't see any other hands raised in the queue. I have a couple of questions, if that's all right. And certainly people are welcome to continue to raise their hands if they have additional questions. We have about 10 minutes left in the discussion and Q&A. So I had a question, Saakshi, for you, but I guess for everybody. So Saakshi, you said that for dynamical collapse theories, although we can get one-to-many evolution, we can get many-to-one evolution, and there is some sense that in the long term, these balance out. That seems quite reasonable to me for microscopic quantum mechanical systems. Is that altogether obvious for macroscopic quantum mechanical systems? Because, when we think about, dynamical collapse theories trying to explain our macroscopic experience, right? It's presumably supposed to replicate our experience that we see Copenhagen-like collapse of wave functions when we do measurements. And that doesn't appear to be bidirectional in time, right? So is it obvious that the story is supposed to be like even-handed when it comes to forward and backward time evolution even on macroscopic scale?
I don't think it can be time symmetric on the macroscopic scale for exactly what you mentioned, that one of the attractive qualities of dynamical collapse is that it might underwrite the second law, and it might underwrite, why we see systems decohere or evolve into what look like more likely macrostates. So the point about, let me see if I can pull that up and just go back to the previous presentation. There we go. So the point about this bidirectional symmetry is very much looking at all degrees of freedoms that are part and parcel of the microstates. And this observation really comes about when you observe, right, the behavior of phase space trajectories. If you kind of want to keep Hilbert space aside for a moment, where deterministic evolution, of course, satisfies Liouville's theorem. Phase space volume is going to be conserved because of these continuous one-to-one maps. But when you have a combination of one-to-many and many-to-one maps, the expectation is that your phase space volume is, practically conserved, when you coarse grain over extended time periods, as opposed to looking instantaneously the way you're allowed to do for the deterministic case. And so, of course, because we're talking about phase space volume, this would only be true for microstates, and we're not looking at anything like the increase in phase space volume because of macroscopic indeterminism.
Right. So
And then,
I was saying, because then my question is, we would expect in a theory like that, that for macroscopic objects, we might see what looks like time asymmetric evolution in some, for macroscopic systems. Of course, we would also expect that in the theory, all those processes could in principle happen in reverse, right? So we would predict that there should be white hole solutions that undergo reverse Hawking radiation, although maybe we won't see those, maybe because of the initial conditions of the universe, those things won't ever occur. But as long as the theory can accommodate those, time reversed macroscopic solutions as possibilities, then overall we are preserving the overall time asymmetry at the fundamental level. But for macroscopic systems, we can see what looks like time asymmetry. So I guess my question is, black holes are macroscopic systems, at least astrophysical black holes, the kinds that we're talking about when we talk about black hole information loss. So is it obvious then that dynamical collapse theories, and again, this is not, I'm not advocating dynamical collapse theories, this is for purposes of argumentation, but is it obvious then that dynamical collapse theories, when applied to macroscopic systems like black holes, are not capable of showing the same kind of significant time asymmetry, right? Where you don't get, that it could match on to the kind of behavior that we see with black hole evaporation, right? So we go from, many to one evolution the way that we see with black holes.
So I have to really perform some mental gymnastics to answer that question, thinking of Hawking's original derivation. But if you basically stabilize the Hilbert space, and you do subscribe to a very large Hilbert space, perhaps an unbounded Hilbert space, that purifies your late time radiation with a remnant, or because and I'm thinking about that strategy because it seems like, at least with Penrose's model, that's the most natural fit. I don't think there's any conflict between the time averaged conservation of phase space value of phase space volume. But if you now want to use the quantum probabilities to apply a measure over microstates, where you realize that the thermodynamic entropy of Hawking radiation is much larger than the initial thermodynamic entropy of the black hole, it's not obvious to me why those stories couldn't be compatible.
Yeah. And granted, of course, this doesn't address your more fundamental point about black hole evaporation being this question about counting up, degrees of freedom before and degrees of freedom after. Dynamical collapse theories aren't directly getting at that. I guess I was just more narrowly asking about, is it enough to say that is it enough just to point to the fact that on average, you have a balance between many to one and one to many, if that's enough to rule it out, or if you really have to appeal to this kinematical versus dynamical argument. So we have about 2 minutes left. Lev, I see your hand raised. Is this a new hand or was it an old hand?
I just want to comment on your question that I believe the good collapse models and the models which we have are pretty good. They are supposed to work efficiently only when there is a measurement type situation. So if there are micros, if there are no kind of no measurement type situation, and the black hole is not necessarily black measurement type situation, so it's not, that doesn't shed much light here. So there's
Great. Thanks, Lev. I appreciate very much the clarification. So it looks like we have about 1 minute left. I don't see any further hands. We did start the discussion Q&A a little bit early. So if it's all right with everybody, maybe we'll call things to a close right now. I want to thank Saakshi again for a wonderful talk and leading a fabulous discussion Q&A. And I want to thank all of you for participating in today's seminar and also in the seminars we've had this entire academic year. Again, we're going to be going on summer hiatus and we'll be returning in the fall with more seminars in the series. So stay tuned for emails about that. In the meantime, have wonderful summers. I hope to hear from many of you at some point during the summer. I know many of us have lots of conversations that are ongoing. And have a lovely summer and best of luck on the fall. It's good to see you all.